Alright, so last time we had talked about this neural networks and neural network verification. So today's class will mostly be an introduction to what DNNs are and a very sort of a slice of what machine learning is supposed to be. Right? So in ML there is a lot more things than I'm going to talk about here because it's usually a course's worth of things, whereas this is only one lecture. But this will mostly cover some of the basics concepts that you need to know to train a neural network and use a neural network and such. Okay. So yeah. So let's come to the things. So so the idea behind machine learning is that there is a number of problems which are difficult for standard algorithms to solve. Right. So an example, a typical example is, let's say that you have a problem where you want to write a program to identify a picture of a cat. Like the program should take and is input some image, and then it should tell you whether there is a cat in the image or not. Right? This is now if you imagine that you are going to sit down and write some program in C, C++ or Python that is going to do this without using any neural networks or machine learning or anything like that. You can imagine that this is going to be really difficult, right? Because first of all, whenever you're writing a program, you need a very solid definition of whatever like it is that you're trying to identify, right? What is a cat? We can't really have like a mathematical or algorithmic definition which characterizes a cat, right? You could say things like, okay, we'll start with the eyes and so on, but the eyes can have different lighting, it can have different shades, it can have different colors, it can look various different ways, right? So there's a lot of such complications and parameters involved that if you were to actually sit down and write this program manually, you'll soon be overwhelmed with the complexity of it, right? So, to actually do this cat identification program, standard like algorithms or, just this normal way of writing code straight up using some C or C++ or whatever language that you have, that usually doesn't work, right? So what we need to do on the other hand, okay. Yeah. Right. Okay. Sure. So so as I was saying, some problem like identifying a picture of a cat is actually very difficult to do using like normal programming, right? If you just think about writing some program, some step-by-step algorithm to identify a cat, that is really difficult to do because there is no clear definition of what constitutes as a cat that you can actually express in some mathematical form, right? There's so much variables, so many variables, so much complexity, things like lighting, shading, the shape of the cat's face and so on. All of those things can be different, and so it's essentially hard for standard algorithms to do these problems, right? But it's very easy for us humans. So there must be some way that a detection of a cat is actually possible to do because we do it, like, right? There is some mechanism inside your brain that does it. So it can't be an impossible thing that that cannot be solved, right? But let's look at it. What do we humans do? How do we know how to identify a cat? Well, we learn how to do it, right? So as child grows from a baby slowly into a child and then an adult, hopefully in the case of identifying cats fairly early on in his life, he would have seen a lot of cats, right? And whenever he sees a cat, his or her mother would probably point out and say that, okay, look, that is called a cat, right? So as we grow, we would see several in such examples of cats, right? If you think about the number of total examples of cat you have seen throughout your entire life, it's a huge number. Even if you think, okay, you have a 2-3 year old baby, even the baby sees some huge number of examples of cats, right? So what we do as humans essentially is we usually learn from examples, right? Somehow we look at examples and we automatically get an idea of what this cat thing is, right? So the good news is we do have a lot of examples of images of cat. Like if you go into Google and you search cat under Google image search, you'll probably get like thousands of results. You can scrape all of that and make this huge folder with thousands or tens of thousands of images of cats with various variety in it, right? So we don't have any lack of examples. So this is a problem where we have a lot of examples of, what we want this program to do or what we want the solution to be, but we don't really have any good like standard algorithm for doing it, right? So machine learning in general is basically tries to solve such problems where you have a lot of examples, but you don't really have any clear step-by-step algorithmic way of solving things, right? So machine learning it tries to find general algorithms. So not just for cat, but it should work for dogs and other things, and much more general than that, not just image identification, right? And it tries to find general algorithms which will somehow learn to solve certain problems from examples, similar or at least inspired by the way we humans seem to be able to learn to solve problems just by looking at examples, right? So that is the entire idea behind machine learning. You have this whole huge set of examples, and somehow we are going to try and learn to solve some problem from these examples, right? So that is basically the idea behind machine learning, and the most sort of the thing which turns out to be the most useful in machine learning in modern day applications, which makes it very ubiquitous, is that you don't really need to understand to use a machine learning algorithm. You need to sort of understand the theory a little bit behind it, true, but you don't really need to understand what exactly the algorithm is learning to do, right? Like I can give you some app that identifies cats, and if you look into its code, you'll find that okay, there is something maybe which is called a neural network. You don't need to pry that open and understand it step by step what that network is exactly doing for even creating that network or working with that network, right? So there is a lot of detail that we can actually black box with a lot of machine learning techniques, and that is what makes it really easy to apply in various situations, right? Because if you have a really complicated problem like identifying the image of a cat, which is, if you really sit down and think about it, it's kind of really complicated. You don't need to really go into the details of, okay, do I need to partition the face of the cat into mouth and whiskers and eyes? You don't need to think about details at all. All of that is somehow automatically handled by the machine learning algorithm, and the algorithm learns to do all of this from examples, right? So that is what I mean by, the algorithm should be general. So this is sort of the motivation and idea behind machine learning. And of course, with this sort of generality, there will come some pitfalls which we'll probably see in the next lecture. But the idea is that you don't need to know what a cat even is. You just need to have some images of cats, and somehow this machine learning algorithm will give you a program that identifies images of cats, right? So how? So to answer this, how we will basically slowly unpack sort of the machine learning paradigm using some abstract symbols and parallelly with another example. So I'll have sort of one slide which will have some symbols like this, and then another slide which will have some examples, and hopefully we'll get an idea by the end of this. But to do that, we'll answer like questions one at a time. The first question which I want to sort of ask is, what does machine learning algorithm even learn, right? So like if I ask you what a program is, you probably have a very concrete idea of it, right? You can say that okay, it's some steps, some sets of instructions, a sequence of instructions, and you might have loops, you might have branches, you might have all of those things, right? But what is a machine learning algorithm fundamentally? What does it learn, right? What it learns usually is something called parameterized function approximators. So remember that what we want at the end of the day is almost always can be expressed as a function, right? So for the cat example, your function will somehow take an image and output like, is it a cat or is it not a cat, right? With machine learning, we have what we learn is such a function which will take some input, give you some output, but other than that, it also has this special thing called set of parameters, right? And the idea is that the behavior of the function is somehow dependent on the value of theta. If you change theta, the way that the function behaves will slowly change, right? So let's look at a few examples of such parameterized function approximators. The simplest example is probably linear functions. So for example, if you think about this, if you keep, theta m and theta c to be constant, then as a function of x, this is just a linear function, right? All we are saying here is that, okay, you have some situation where you're saying output ax plus b, right? So you're saying y is equal to ax plus b. But also you're putting this theta m and theta c in the parameters, which means that if you change theta m and theta c, your a and b's are basically changing. Then what exact linear function you have is slowly changing, right? So in some sense, these parameters are governing. So if you think of your linear function as being something like a line, or a graph of your function is something like a line like this, then your parameter is going to slowly change the, where is this line, how high, what is the slope of the line, all of those things this parameter will change. So maybe you can change your parameter and shift the line from here to here, or shift it from here to there, right? So you can slowly change your parameters and shift the way or change the way that your function behaves. But as a function, again, it's just something that takes in x and outputs y, and in this case it's just something that takes in x and computes a linear expression and outputs y, right? So that is the sort of simplest example, but you can take this idea and make it much more complicated, right? So for example, you can have quadratic functions. So instead of having just, two parameters, two real parameters, I can have three real parameters, right? So I can have something like theta naught for the constant term, theta 1 for coefficient of x, and theta 2 for coefficient of x squared. And again, we are going to, if we were to graph this function for any specific value of theta, we would again get something like this, right? Some parabola like this. But as you change theta, maybe the shape of this parabola will change, right? You can shift the shape down here and then up here by changing theta appropriately, and you can do this gradually as well, right? So this is basically the idea behind parameterized function approximators, and in most cases a machine learning algorithm, if you look at it, the output is usually some parameterized function approximator with like a concrete value of this parameter. So it will give you some f, and it will give you some concrete value of theta. So then to run this, you just plug in whatever input you have x, and this will output the y for you. Okay. So far, is there any question? If not, then say no. Is there something in the chat that I'm missing? Okay, sure. So no questions? Okay, so this is basically the idea of parameterized function approximators. So now what we are going to look at is one very specific parameterized function approximator, which is called deep neural network, right? And there are many other parameterized function approximators. In fact, people use linear functions, people use polynomials, people use a lot of different things, but we are going to focus on deep neural networks. And as it turns out, these DNNs are actually very powerful on their own right, and we're going to look at some intuition as to why or in what sense they are powerful. But like right now, usually when people say they're using machine learning, almost always they refer to deep learning, which means that what they're using is deep neural networks in some capacity, right? Not always, but almost always. So deep neural networks are sort of a very important class of parameterized function approximators. So what is a deep neural network? So one way to think about this is like a graph, right? So we have this sort of a graph here. So each one of these nodes, these are called neurons, right? So this sort of graph will take in as input some pair of real numbers in this case, right? Some vector of real numbers will take in as input. So for example, if you look at this one, it's going to take in some two real numbers here as input, right? So you're going to feed in, say, x1 over here and x0 over here, right? So in this sense, you're feeding in this vector x0, x1 as an input to this function, right? So then what happens is somehow it's going to compute an output from these two nodes or neurons, right? It's going to compute an output, and let's just call it y0 and y1. Okay, so in general, neural networks take vectors and output vectors. The vectors can have, the input and output vectors can have any size. In this particular case, both of them are two-dimensional because we have two neurons each here. But again, like you can have much more larger networks. They can have any size in general, right? So now, how is this computation actually being done in the neural network, right? So what happens is that if you look at each one of these edges, each edges will have an associated weight with it, right? And what happens is that the value that is there in this particular neuron is going to get passed along this edge multiplied by this weight. So the value that is going to go along this edge is going to be W, which is this weight, times x naught, right? Similarly, if we have, say, let's call this one W naught, so W naught x naught. Similarly, along this one, it might become, along this edge, you will have another weight W1 and you will get W1 x1 because x1 is coming here. Similarly, along this edge, you will get, another weight, so you'll have, say, W2 x naught. So in this way, each one of these edges has some weight, and you end up multiplying these weights when you basically what you do is you pass the value through the edge and multiply these weights, right? So then at this neuron, you now have a weighted, a multiple weighted values coming in, right? So you have got W naught x naught coming in from this edge. There's also this particular edge over here. So this particular edge is going to have some other such value here. So it's going to have some, say, W3, whatever, some index. Okay, actually I have labeled it as W1 already. So W1 x1, right? So you've got such two values coming in here into this neuron. So what's going to happen there is that we're going to add up all of these values. So what you end up doing is you end up computing a weighted sum of the values from the previous layer. So each one of these sort of lines of neurons are layers, right? And layers are arranged in this way, and you have connections from one layer to the next layer. Usually you don't have connections that skip layers, right? Although there's nothing in particular stopping you, but let's keep things simple. Think that connections are from one layer to the next layer to the next layer and so on, right? So you will have such layers, and what each neuron gets is such a this kind of a weighted sum of the values coming from the previous layer, right? Then what it will do is it will do two things. It will firstly add a bias to this, right? Maybe I should use a different color. Yeah, so it will add a bias to all of this. So then there will be some value called B, which is going to add to this weighted sum. So now you have a weighted and biased sum. Finally, it's going to take this entire thing and apply some nonlinear activation function on it, right? We call this nonlinear function activation function, but in general it can be very wide class of well enough behaved functions can be applied over here, right? So for now, let's say that this function is something like a sigmoid. Sorry. Right? So in general, it can be sort of any non-linear functions. Linear functions are usually not, they don't give rise to good behavior or rich enough behavior, but usually people use some sort of a non-linear function. And one of the examples is sigmoid. There is another much more common example which we'll look at later on, but for now let's think about sigmoid. So you're going to apply some non-linear activation function, right? Okay, so by the way, is everyone okay? So sigmoid function basically is some function whose graph looks like this, right? So it's between 0 and 1, and as you go to negative infinity it goes close to 0, and as you go to positive infinity it goes close to 1, right? And then there is a smooth rise somewhere around 0 when the input is 0. So it will apply some sort of a function like this to this weighted sum, and then this repeats layer by layer, right? So the output of this neuron, the value at this neuron, if you will, is basically sigmoid of this weighted and biased sum, and then that value is again going to be multiplied by the weights along this edge, along this edge, and so on. And again each neuron here is going to receive a weighted sum, and again it's going to add a bias, and again it's going to put the entire thing to a sigmoid, right? And this is going to happen over and over again through each one of the layers in your neuron until you finally get some value at the output layer, right? So this is basically what a neural network is and how it computes things. So as a structure, as a thing that, like, as an object that performs some computations, is this does this make sense? Yeah, alright. Specifically the people who haven't seen DNNs before, so does it make sense for them as well? Yeah, okay, sure. Okay, so this is basically the idea. You take sort of a weighted sum, add some bias, apply some nonlinear activation function, and you do it again and again, layer by layer, right? So remember, what we are looking for is a parametrized function approximator, right? So it should basically look something like this, right? It should be something that takes in an input. You also have a set of parameters, right? So far, the input is fine, right? It's going to take in some vector like this as input. Okay, so by the way, as a notation, in my slide, whenever I have something in bold, whenever I have a symbol in bold, it usually is a vector of real numbers, right? So for example, here y is a vector, x is a vector, theta is a vector, right? So here, the fact that it takes in a vector as input is clear. The fact that it puts something out as an output is also clear. But what are the parameters? So the parameters are going to be these weights and bias values, right? So remember that for each one of these neurons, you have, or for each one of the edges, let's say, you have a weight associated with an edge, right? So each one of these weights is going to be part of your parameter. And again, for each neuron, you have a bias value that you're adding in, right? So that bias value is also going to be a part of the parameter. So your parameter, or set of parameters, or parameter vector, or however you want to say it, theta, this entire theta vector, it's going to be this huge vector which is going to contain all the weights, so on, and all the biases, so on, collected from the entire network. So your theta basically looks like this huge collection of weight values and bias values, right? So these are what your parameters are, weights and bias. And like in the case of this linear and quadratic sort of parameters function approximators, there when we are changing our set of parameters or list of parameters, we were getting, the shape of the function was, or the behavior of the function was changing accordingly, right? Here also it will be the same, right? If you change these weights, if you change the values of these weights, then you'll get a different weighted sum at this neuron, right? And then again the output of this neuron is going to be different, and that's going to affect the values at these neurons and these neurons, and finally you'll get a different output over here, right? Similarly, if you change the bias anywhere in the network, everything downstream from there, all those values will get changed and you'll get a different value here. Now it's hard to imagine how exactly this for linear and quadratic things, where those objects are sort of familiar to us in a way that you can, at least for linear things, definitely you can have an intuition as to, if you change the parameters, then the graph of your function changes in this way. Here this object is much more complicated, so you might not have an intuition as to what this will look like if you change the parameters. But just notice that you can just take these weights and bias values as parameters, and if you change them, the behavior of the function changes, right? So is this okay to everyone? Yes, no? Yeah. So the fact that this is a parameterized function approximator is clear to everyone, right? Okay, so now we have defined this sort of complicated, parameterized function approximator, which we are calling a deep neural network, right? I want you to notice one thing here, that if you consider this deep neural network as a function, this is actually subject to certain things. But let's say that if your activation function is actually just sigmoid, you can have other activation functions here as well. But if your activation function is just sigmoid, then sigmoid is a smooth and continuous function, right? In fact, it is a smooth function. So then this entire neural network behaves like a smooth function, right? It's smooth in terms of the inputs, and it's also smooth in terms of the parameters. So if you change your parameters, this entire output of the function for a given fixed input, let's say, the output will also change in a continuous way. That change will also be differentiable, and so on, right? So this is actually continuous. So I should say usually, because it depends on what, like if you have something other than sigmoid here, it's not going to, it may not be so nice, but usually this is continuous and differentiable with respect to x and theta, right? So does this, again, is this clear to everyone? Does this make sense? Okay, sure. So far so good. So then let's move on to some example and some intuition. Okay, so we have this complicated object which we are calling a deep neural network. Can we get any intuition as to sort of what it's doing? So let's look at an example, and we'll use this sort of as a running example, and later on maybe we'll even have an assignment where you actually will get to work on this. So by the way, this is alright, so I'll say that later on. But let's consider a simple task, right? So we have a task where we are trying to identify handwritten digits, right? So for example, I've given 9 sort of pictures of handwritten digits, and as you can see that identifying things here is kind of difficult, right? It's again, like, it's not a very standardized font. For example, you have 3 ones here, and all of those 3 ones looks kind of different, right? So this one has got a little bulb sort of a section down there. This one is kind of diagonal, right? You've got 2 7s. One of these 7s has a nip here, the other one doesn't, but the other one has this sort of cut in the middle, right? Then you can have such variations. The 4, for example, it's sort of, if you look at it, it's kind of protruding out like this over here, whereas you can imagine another person might write it like this and join it, in fact, right? So there is a lot of variation that will come when you start to identify handwritten digits. So somebody might even write one like this instead of writing it like this, or writing it like this, right? So there is a lot of variation, and look at this thing, right? It's not even a circle. So how do you actually identify these digits? And it's kind of the sort of problem where like just trying to sit down and think of an algorithm doesn't really work. It's kind of like identifying a cat. Like if I give you some handwritten digits, and the handwriting is not, like, it's not illegible. As humans we can all identify these digits, but it's also not like perfect calligraphy, right? So it's a hard problem, and it's sort of a problem where applying machine learning, or specifically in our case neural networks, makes sense. So okay, so let's consider this simple task. So again, here our input is going to be an image, right? But how exactly, right? So the image is nothing but an array of, or a 2D grid of pixels, right? So it's a 2D grid of pixels. And each pixel, if you consider the image to be black and white, each pixel is going to be a value between 0 and 1, right? So let's say 0 means black and 1 means white, right? So it's going to be some value between 0 and 1. So 0.5 would be a gray that is exactly, halfway between those two things. 0.75 would be like lighter, 0.25 would be darker, and so on, right? So an image is then nothing but a 2D grid of these real values, right? So an image is basically just going to be this huge vector of real values. Like if you flatten this 2D grid and if you somehow index this 2D grid and say that okay, so if I have a 2D grid like this, right, some grid like this, and I say that okay, this is 0, this is 0th component, this is the first component, second, third, fourth, and then fifth, and then so on, right? So in that way you can sort of index each one of your pixels, and each one of these pixels has a value between 0 and 1. So what you get at the end of the day is an array of these real numbers. So you can think of that as a vector of real values, right? So again, it's clear that an input is an image, and that image is a vector of reals, right? Is this clear? Yes, no, something. Okay. Yeah, so about recording, I am recording. So I don't know if there is some other way to record, like specifically within Google Meet, but I am using a separate app to record my screen and my voice. So so yeah, hopefully that will work out well, and we'll have a recording at the end. And okay, so it's clear, I'm assuming. Any questions? Okay, fine. So so yeah, we have an input which is an image, but we can encode it like a vector of reals. Similarly, in output, our output is supposed to be, what digit is this, right? So we have again 10 options, right? 0 to 9. So we have 10 options here. So what we ask our neural network to do is to give a score to each one of these options, and a higher score is going to correspond to the neural network telling us that it thinks that it's probably this digit, right? So if, for example, output is also going to be, so output is going to be this bunch of scores. So then if say 0 gets a high score, so if 0 gets a score of say something like 1, whereas everybody else gets a score of say 0.01, then we know that the neural network is telling us that okay, I'm really confident that this digit is 0, definitely it's 0, right? So output similarly is going to sort of be this sort of a vector as well, right? And this vector is going to have a score for each digit, right? So maybe the first component of the vector corresponds to the score for 0, second component for 1, and so on, right? So this is basically what the inputs and outputs is going to be for neural network. Then what we sort of intuitively expect to happen is that at each layer we'll sort of compute patterns of higher and higher level of detail. So what do I mean by that? So at the first layer, the right after the input layer, at the first layer, so if you can think of it as at this layer, right? So maybe yeah, so at this layer what you'll end up getting is some very simple low level patterns, right? So some things like lines, right, curves, and so on. So this layer maybe is going to have say some 50 or 100 neurons, and each one of those neurons is going to basically have a score saying okay, the upper left corner of the image has a line, right? So maybe whether or not this part of the image has a line that goes like this, you'll have one neuron dedicated to that in the first layer, right? Similarly, in the first layer you're going to have another neuron which is going to be dedicated to okay, is there a curve in this part of the image that looks something like this, right? So you're going to get these low level patterns like lines, curves, etc. in the first layer. The second layer is now going to get the first layer as input, right? So the second layer gets some input like okay, I know that there is a line here. So the second layer will probably get an input something like I know that there is a line here, and I know that there is a curve here, and I know that there is a curve here, right? So what it can try to do is it can try to take these lines and maybe combine them to form shapes, right? So for example, if the second layer gets an input like okay, the neuron that corresponds to there being a line here has a high value, and similarly a neuron corresponding to a line being here is a high value, and we have a third neuron corresponding to a line being here as a high value. So then the second layer gets this sort of information, right? So it can basically get that information and combine them to form a little bit more higher level things, like say shapes, like what is this triangle, a circle, and so on, right? So maybe it can combine three curves that looks like this to form something that is roughly a triangle, or roughly a circle, or three lines like this to get something that is roughly a triangle, and so on, right? So intuitively we can think that the second layer is combining the information from the first layer, which has got very simple sort of lines, curves, and so on, and it's combining to make circles and triangles and so on, right? So then the third layer can basically get to combine that information, right? So the third layer gets information that, okay, I have a circle here, I have a line here. So what the third layer sees is something like this, you know. And again, it doesn't exactly see these lines and circles, but it sees neurons encoding these things having high values, right? The third layer sees a neuron encoding a circle here having a high value, and it sees a neuron encoding a line sitting close by having a high value, right? So something like this, right? Or maybe something like this. So when the third layer sees these two things, it can then say that, okay, if there is a circle here and there is a line here, that is, if this neuron has a high value, I can combine that to get digit, right? I can combine that to say that, okay, this is actually the digit 9, right? So the third layer is going to combine these shapes to get some digits. So this is basically the intuition with which people, started even exploring these neural networks like structures, right? The idea being that, there are these problems have these sort of levels of abstraction into which we can split them. And then each one of these levels of abstraction we can sort of delegate to simpler computations, and then a composition of these simple computations gives us this function that can actually identify complicated shapes like digits and so on, right? So that is basically sort of the intuition, or one of the intuitions that you can think of, like that you can keep in mind when talking about neural networks. Like, this is about levels of abstraction. Yeah. So any questions so far? Yes, no? Okay. Alright, so this is basically the intuition behind neural networks. So now we come to the second part of the equation. So first part is that, okay, we do have some neural networks. So we have some parametric function approximator, right? That is, we have some huge complicated f, which is, some f, x, theta. Now all of those things which I talked about before, or in all of those things we sort of assume that somehow we have a theta that actually encodes shapes properly, or encodes lines and curves properly, right? But if you just have some random theta, you can't expect that to happen. A random theta is just going to take your image and give you some random output, right? So of course the entire point of ML is to find a good theta. And what can we use to find a good theta? The examples, that is the data, right? So how do we do that? Almost all ML algorithms, the way that they do that is at some level they define something that is called a loss function, right? So let's just call that L theta, and again they define this based on the examples. And then what they do is, okay, so this is, I missed the bold over here, this is a vector. But what they do is essentially they've tried to find a theta that minimizes the loss. So they frame this entire problem of finding a good function as an optimization problem. So machine learning algorithms almost always reduce things to an optimization problem, right? So the entire idea is to somehow find this loss function which characterizes the way we want our f to behave, and then try and optimize it or minimize it, or find a good theta that minimizes that, right? So how do you define L? That is actually in some sense the crux of a lot of ML algorithms, and it's a case by case thing. It's somewhat complicated, but we'll look at a very general class of things called supervised learning. But in general, depending upon how do we define L, we have a few categories. So first is this thing called supervised learning. So remember, whenever we're defining L, what we're trying to do is we're trying to get some statistical measure of how good we are performing on whatever examples that we have, right? So the simplest way you can think of doing that is that, okay, your examples are nothing but some inputs and expected outputs, right? So you have this huge list of, you have x0, y0, x1, y1. So you have this huge list of such pairs of input and output values, right? And then if you have all of these, then you can sort of define your L as the average error that you're getting for a given theta on all of these, right? So again, your F you have, right? So you can do something like this. So you can take an average over all of your xi's for a given theta. You're taking all of the xi's that you have, that is all of the input examples that you have, and this is giving you some output. You're subtracting this expected output from it, taking the absolute value maybe, or some measure of distance, and then maybe you're taking an average over all of this, right? So n is, say, the number of such input pairs that you have. So some average like this will basically sort of tell you on average how often do you make an error, right? So this is the basic idea behind supervised learning, where you have input, you have all your outputs, you have this, crucially you have these yi's. So you can express your loss as being how poorly or how close is your output of the F in general on average to all of the outputs that you know of, right? So again, this is a function just in theta, right? Because xi's and y's here are actually constants that come from this huge list. So you can define L theta to be this, and then you can somehow try and minimize this, right? So is there any questions so far? Yes, no? Okay, sure. So this is basically the case in supervised learning. In unsupervised learning, things are a little bit more complicated, and we won't go into it. But the unsupervised learning problem is basically stated as usually when you only have input. So you don't know what your output should be. You don't have these things. So these things are not available to you in unsupervised learning, right? So if you don't have these things, then how do you define loss? It's a little bit more complicated, but you can still do things. So there are these things called encoders, where you try to take some input, say an image, and try to somehow pass it through a DNN to compress it, right? To get some compressed image. So then usually what you have is this compressing DNN is called an encoder, and then you will have another DNN that will return you the original image, which is called a decoder. And this compressed version is some abstract thing, like it's some vector. You don't really know what an actual compression of an image should be, right? So you don't really, for a given image, you don't really have its corresponding compressed version. But what you do have is these two DNNs, encoder and decoder. And what you can do is you can check if I pass it through the encoder and then again decode it, do I get back something that is close to the previous image or not, right? So you can check the average error between, so you encode it first, get something compressed, and then decode, get something uncompressed again, and then if this is your x, you can call this x cap or x hat. Then you sort of take the average difference between x and x hat, right? So you can have a loss function like this. So there are like many more. Yeah. Oh yeah, sure. Yeah, so for the unsupervised learning, what you sort of the general unsupervised learning paradigm is that you don't really have an output, right? So again, unsupervised learning, there is several examples, but let's focus on this one example that I was talking about, where say you have some. Okay, so maybe I'll go into a new slide here, right? So maybe say you have some algorithm which you want to use to compress images, right? So you want a lossy compression using DNNs. Let's say that is your problem, right? So then, what you're looking for is some DNN that will take in an image, and then there is a compressor. This is a DNN, and then somehow it's going to output a compressed version of this image, right? Now you don't really expect to know what this compressed version is supposed to be, right? So like, if I, for example, you're trying to find out this DNN, right? You're trying to learn this DNN. It's not like you have a standard compression algorithm so that you can say that, okay, it's a, this is a zip file or a, JPG file, and this is how the compressed image is supposed to look like. If you don't even know what your compression algorithm is, because your compression algorithm essentially is the DNN that you're trying to learn, then how can you know what your expected Y is, right? So you can have this huge set of images that you, like some database of images that you have. So you can have x0, x1, and so on, this huge set of images, but you don't have these corresponding compressed versions, right? Because you don't know what sort of compressed version your algorithm is supposed to produce. So then this is an example of unsupervised learning, where you have the inputs but you don't have the outputs, right? So then how do you characterize in terms of the loss function what your compressor is supposed to do, right? So in this particular case, the way people do it is that they have an expander as well. So this compressor is usually called an encoder, and they have a decoder, and this is also a DNN, right? So then what they do is basically they'll take your input, because you have your input, they'll pass it to the encoder, they get some compressed version, and then pass that to the decoder again, and you get back some x prime, let's say, right? So then you know that the way that your compression algorithm is supposed to behave is that your encoder should, like your decoder should basically be the inverse of your encoder, right? So that is, x prime should be equal to x. That is the expected behavior. So you encode that into your loss function. So you say that loss is basically the average distance between x prime and x, right? So essentially the idea is that you want to encode the expected behavior of your function as a loss. It's very simple if you have a bunch of input-output example pairs, but if you don't, then you sort of try and find some other property that you can, encode as a statistical property into your loss, right? So does this example of a unsupervised learning at least make sense? This encoder-decoded example? Okay, so yeah, so as you can imagine, there are other sort of unsupervised learning problems where maybe even this doesn't work. Like then you have to use other things. Clustering is an example of an unsupervised problem, for instance, and there again you have to use other measures of whether things are suitably clustered or not. So there is a lot of things there which I'll not go into. And then there are other paradigms like reinforcement learning, which I'm going to name drop and leave it at there because we decided that we're not going to go into that in this course here. But yeah, basically supervised learning is like the assignment will mostly be an example of supervised learning itself, and if we have to train other artifacts or other more complicated neural networks at some point, when even then I think mostly will fall within the paradigm of supervised learning itself, right? So remember that we are trying to verify neural networks at the end of the day. We're not trying to train them, so I'm not going into all of the other kinds of machine learning paradigms that are there, right? So yeah, so if that is okay, then let's see what this sort of supervised learning framework looks like for our image or digit recognition example, right? Is that okay? Yeah, sure. Okay, sure. So again, so in our digit recognition example, what do we have? We have many input images, right? some huge set of input images xj, so x0 x1 up to some huge, usually it's, I think, so we have, there is a database called the MNIST database, which is basically a lot of grads, I think undergrad students or something like that, they were made to write a bunch of digits and then label them what digits they are. So it's a labeled data set of handwritten digits. I think it's got around 60k like images in there. Then similarly we have a output label for each one of them, right? And this output label tells us what digit it is. So what we'll basically do is we'll treat this output label as a probability distribution, right? So if you think about one digit or this one particular image, then you can say that, okay, you can ask the question, what is the probability that this image is 0, or what is the probability that this image is 1, right? So in some sense, each image has a corresponding distribution with respect to it, which basically characterizes what digits it can be, right? So for example, if I take this digit 5, if this is my image, then I have a corresponding probability distribution which assigns probabilities to this digit being 0, this digit being 1, and so on. Now I know that this digit is 5, I know that this is labeled 5, so I'm going to basically define my correct probability distribution or output label or output probability distribution, this output label, as being, okay, it's a probability distribution where the probability of this particular image being 0 is 0, probability of this particular image being 1 is 0, and so on, but the probability of this particular image being 5 is 1, and then with being anything else is 0, right? So we basically have as an output, or as a correct output, we have this sort of a probability distribution where, you know, whatever actual value or whatever actual digit this image represents, that particular value has got probability 1, everything else has probability 0, right? So this is what we have. We have such images and we have such vectors representing probability distributions where again one component is 1, everything else is 0, right? So we have images and then correct probability, some expected probabilities, right? Or expected or correct output, which is a probability distribution. So now similarly our DNN is going to also like take in this image and output as some score, right? So output is a set of scores. So a priori these scores are like, it's going to be just some random numbers. It's just that the number is greater means that the image has a better chance of like if the output is greater for 5, then the image has a better chance of being 5. The DNN thinks that there is more chance that this particular image is 5, right? So the output is such scores. So then we need to or it is good if we can somehow convert that into probabilities. So then we can express what the DNN thinks about this particular image as a probability distribution, and we can leverage there is sort of a mathematical theory about distances between probability distributions and so on, and we can use that to build our loss function, right? So what we do, or what we use, sorry, this won't be sigmoid, I'm sorry, this will be softmax, but there's this particular function called softmax that we use to convert these scores into probabilities, which looks something like this, right? So each score is basically converted into a value like this, and then you finally normalize it by the sum over all of the scores, right? Sum over this thing for all of these things. Sorry. Right? So then what you get is basically a normalized proper probability distribution, right? So now why this particular function? There is some motivation. Basically the good thing about this function is that it can actually work with any kind of scores, right? Your score can be positive, your score can be negative, it doesn't matter. And also the probability distribution that this function outputs is always going to have non-zero probabilities. Even if the probabilities are very small for a particular digit, it's always going to be non-zero. And that's good, because if that turns out to be the correct answer, we at least can start from somewhere. It's not like the neural network has completely shut off that particular probability at all, right? So it allows the neural network to basically say that, okay, there is a tiny probability, and then we can say that, okay, that tiny probability is actually correct, increase that slightly. Whereas if it's zero, because of the ways these machine learning algorithms work, it can get stuck at zero, right? And it's okay, you think it's nothing, then we really don't have any scope of improvement there. So yeah, so now we have these probabilities, and now then our second step is basically to compute some notion of distance between the correct probabilities and the probabilities that we have, right? So we have one distribution which is this correct distribution, P0, P9, and then we have this P0 hat to P9 hat, which represents our distribution, the output distribution from a neural network, and we have to somehow find the distance, some measure of distance between them. So what we use is something that is called cross entropy, and this comes from information theory. But what basically happens is that this particular cross entropy value, this will basically get minimized. Sorry, again there will be a negative here. But this will basically get minimized if your distribution is actually matching with the output distribution, or with the correct distribution, right? So the more distance there is between the correct distribution, which is this one, and the so the more there is a distance between this distribution and this distribution, the lower that this particular value will be, and when they match, the higher that this particular value will be, and then they match, this value will basically come at its minimum, right? So then with this we have some measure of distance between these two distributions, and then once we take an average of this over all of the input images that we have, so if we take an average of this cross entropy, then what we get is basically our loss function in this particular case, right? So okay, so I realize that there is a lot of details here, but I just wanted to give you a flavor of what you would do step by step in this particular example, as a sort of something that you can follow. Right? So any questions? Even if you're completely lost, say that I can go over things again. So this makes sense to everyone. So just wondering, the people who have not seen DNNs before, so have you done like some ML course where you have sort of seen all of these things, like non-DNN related ML course where you've seen cross entropy and like softmax? Okay, sure. But all of this makes sense to you, right? Okay, sure. That's great. So then you're catching up really fast, because I feel like I'm going much faster than proper ML course would have, I guess. But yeah. But yeah, so basically this is the idea. The idea essentially is that you somehow take your output of this DNN, you take the expected output, you find a way to compare them, some notion of distance, some norm, if a norm makes sense, if a norm is well behaved enough, and we'll see what that means in the next few slides, what sense of well behavedness there has to be, and then you take an average over all of that, right? And then you get a function that you have to minimize. So far it's clear that we have reduced our function or our problem to minimizing this cell, and we have seen how we can define this cell precisely, right? So we have actually some precise sort of concrete definition of what this cell should be, and we have reduced our problem to minimize L. So how do you actually minimize L in a way that is general and does not depend on any assumptions about L, right? Because see, L, what is L, right? How do we optimize L? What do we know about L that we can use to optimize L, right? So we know some things, but what we know is actually not that much in the context of optimization, right? So L, we know that L is actually, since our F, if you remember, our neural network here, this F that we had, we say that this was continuous and differentiable with respect to theta and x, right? Now once we package all of these things here, since F was continuous and differentiable, and what we're doing when we're constructing the loss function is essentially something that looks like this, right? We are essentially doing something like this. Since F is continuous and differentiable with respect to theta, we can actually expect our L to also be continuous and differentiable with respect to theta, right? So what we know about our L is that it is continuous and differentiable with respect to theta, right? But that is also all that we know, because if you had something like F was linear, then you can probably derive some sort of convexity of L, right? If you knew something about how your F is supposed to behave, if you had some handle on that, then you could have maybe said something more about L, where this sort of, you could have approached this in a more general sort or more global way and actually optimized for a global maximum, right? But we don't have anything else about L, right? We don't know what our neural network, or we don't want to think about what a neural network is like. It's some really complicated object that does some computation. We don't want to go in and check, is it convex? It's definitely not linear. Is it convex? It's definitely not convex, probably, right? So we don't have any other handle on L, actually. So we don't know anything else. So then how do we optimize, right? So what we do is we do this sort of, sorry, just a second. So what we use is this algorithm, which is called the gradient descent algorithm, right? And it's actually very simple, and it's surprisingly leads to very good results in practice, but theoretically we don't know, theoretically speaking it shouldn't work, and we don't really have any theoretical handle on why it does work, right? So what the algorithm does is, it's going to calculate the gradient. So it's going to start with some random theta. So initially you have some random theta, right? And then you're going to just calculate the gradient of this L. So you have some del L del theta, right? And then this is essentially going to give you the direction in which L increases the most, right? Since L, remember, theta belongs to some Rn, right? So L is a function from some Rn to R. So then if you take the gradient, it's going to basically give you a vector. So this entire thing is again going to belong to some Rn. And this gives you a direction in which L increases the most, right? So if you take the gradient, it gives the direction in which L increases the most. So what do we do? Since we want to minimize the L, we move slightly, opposite to the gradient. So move a very small amount opposite to the gradient, right? So now we have a new theta. So when we say move slightly, what I mean is that we are going to take this, so let's call this thing as delta, or maybe t, and then we are going to set theta to whatever the previous value of theta was, plus some small delta times, or actually minus, because we're moving in the opposite direction, but yeah, minus some small delta times this g vector, right? So we do an update of theta like this, and then we just repeat. So it turns out that if you keep repeating, you actually end up coming to something that is at least a local minimum, right? So you end up approximating a local minimum, and intuitively that's clear. Like, in fact, the picture is really nice, right? So you can sort of start from here, go down the gradient, it's just going downhill in some sense, right? And you just follow a downhill path all the way until you reach somewhere that is close to a local minimum. But remember that this can only, firstly, there is no guarantee that you'll reach the exact local minimum, right? Once you come close, you can have things like you can overshoot, you can undershoot, right? So once you come close, then all of those things can happen. Sorry about that. So yeah, so once you come close, all of those things can happen. But so like say if you're this close, then you can a gradient update can actually send you here. So you can overshoot and things like that can happen. So it can only approximate, and it can only approximate local minimas. There is no global guarantee here, right? Because it might happen definitely that your function looks something like this, and you start from here, and you end up going here, and you settle over here, right? Whereas this is huge global minima just across a cliff like this, right? So this is sort of one of the mysteries in some sense. A lot of people have approached this in a lot of different ways, but I don't think we have any good enough answer or any rigorous answer. But this does work very well in practice. Maybe it's somehow in practice the kinds of L that we see is actually good for gradient descent. Definitely you can come up very easily with like simple counterexamples where gradient descent shouldn't work for a given L and theta. But if you actually construct a neural network and maybe run gradient descent with say 3 different random values of theta, one of them will come to something very close to a very well performing optimum, right? So we don't really have any idea or way of understanding why or in what sense it does work well in practice, but it gives us good results, right? And this is basically the algorithm that we use. So any questions about gradient descent? Yeah, I just have one more slide. It'll take like 5-6 minutes. That's okay with everyone. Any questions? People are leaving apparently. Okay, sure. Alright, so I think right. So the only thing that is left is basically how do you actually calculate the gradient, right? So I talked about calculating this del L del theta, but how do you do that? So again, there is some details over here which I don't think I have too much time to cover, but the basic idea is that you use chain rule, right? So you can think of this entire neural network as being this really complicated thing, but if you remember, your L is ultimately a function on the output. So if I call this output as y at this particular layer, say the output is this y vector, so L is ultimately some function on y vector, right? So if you try to compute del L del theta, what you'll get is some expression that is going to involve del y del theta, right? And then each one of these, so if you focus on just this one particular neuron, so each del y del theta, what is y in this particular case? Y in this particular case is some sigma applied to some sigma, some weighted sum of previous neurons values plus some bias, right? And you're trying to take it del with respect to theta, right? So then again, remember that this theta actually contains these parameters, right? So if you do this, you will again take some expression that is going to involve del vi, like for each I you're going to get del vi del theta, right? So in this way, if you keep applying chain rule and keep going backwards, you're going to keep getting these expressions that are going to be in terms of the gradients of each one of these neurons values with respect to theta until you finally get to the input layer. And then of course the gradient at the input layer is actually 0, because remember the input in our case is just some constants that we have chosen. Like I say constants, but basically just some data points that we have, right? So when we're doing this differentiation, those data points are fixed. We're not changing them. So the gradient width of those with respect to theta is actually 0, right? So once we get to the input layer, those gradients will come to 0. But as we go back, slowly and slowly, we're going to collect terms like these, and we're going to collect the various terms corresponding to the gradients of the weights and biases into this huge expression. And then, once we have done this entire thing moving backwards, then we'll have this huge expression for our gradients, right? So if I say this like this, like in sort of a fast way, it seems kind of complicated, but I'd urge you to sort of take, say, maybe a very simple neural network, something like this, that has got, say, 6 neurons, and then try and just in pen and paper work out what these gradient expressions will end up looking like, right? And you'll see that they're actually much cleaner than you would expect. And in fact, they can be calculated using very simple matrix algebra. Most of the neural network libraries, they just do some very simple matrix algebra and they can calculate the gradients quite fast. So this calculation of gradients, it turns out to be just a bunch of matrix operations on arguably large matrices, because usually neural networks are large, but it's not some very complicated thing that you have to, or very large amount of expressions that you have to keep refining. Although theoretically it's just applying chain rule and keep going back last layer, keep expressing things in terms of the gradients of the last layer and apply chain rule again and so on, right? So this is sort of the high level concept, and I hope that at least intuitively it's clear that you can do this. I'd say the best way to understand that you can actually do this is try it for a small network like this, and yeah. So that is all I have. Okay, so any questions? Right. So you had forgotten what L and theta are, right? Okay, so by the way, I can hang out here and answer any questions that you have. If you don't have any questions and you don't want to listen to what other people's questions are, you can also leave. I can stay here. So by the way, your name is coming up as D Ghosh. What's your what do we call you? Dhruva Jyoti, acha, okay, nice, good. Alright, so yeah, so sure, so I'll maybe go over what L and theta would, right? So at a high level, this is basically what we have. Sorry. So I'll just give you sort of a recap overview sort of situation, right? So we have some parameterized function approximator, right? This is a neural network. This is some complicated parameterized function approximator that we have, right? But it's some parameterized function approximator. If you want, for now, just think of this as being something that looks like y is equal to theta mx plus theta c, right? So if you want, just think of it like this, right? But it's something more complicated than that, which is a neural network, but that's fine. Now, what we did was, or what we have is, we have these huge table of input and output values, right? This is basically our image and digit, right? So this corresponds to some input. So we have maybe some 60,000 rows here, right? It's a huge number of rows that we have. And similarly, we have some digits. Some labels corresponding to each one, right? So this is what we call our data, or our examples. So now the loss function is basically supposed to characterize what we expect our f to do is that, if we give any of these x0s or xi's to f, what we expect is that if we pass xi to f, then the output should be yi, right? So that is what we expect. The loss function characterizes whether that's happening, or how often that happens, or some statistical measure of how close we are to actually achieving this, and that is your L. So L stands for loss, and that characterizes this thing, right? So how would you say, how would you say that, okay, how close is this particular f to actually producing yi when given input xi, right? So you can simply say that, okay, if I give input xi, and remember everything, whenever we talk about f, there is always this parameter theta there, but we can always say that, okay, if we give input xi, whatever output it produces, you can always think about the distance of this f of xi from yi, right? So there is this, so ignore this part for now. Maybe if I'll write it like this. This is just some function, right? So we can always take this distance, and then for this particular xi, this gives us whether our function is, if this distance is 0, then we know that our function is behaving as it should on this particular xi, right? So then if we take an average of all of these over all our i's, right, so all the images and all the digits, then we know that, okay, our function is behaving as it should, at least from what we can see from our examples, right? So if this entire average is 0, we know that our function is behaving as it should, like, then we can be satisfied with our function, right? So does this make sense so far? Right. So then let's bring this theta back in, right? So remember that these x0s to xn's and y0s to yn, this is some like huge data set, but essentially they're just constants. We have some huge number of constants, sure, but they're constants as far as we are concerned, mathematically speaking, right? So if we bring our theta back in, then in this expression the only variable we have is theta, right? Does that make sense? Yeah. So then this entire thing is a function of theta. We call that the loss function, right? So this loss function characterizes the way f, or the what we want f to do, and that is a function just of theta, right? So if we can find a theta for which our loss function is 0, then we are good, right? Is that okay? Yeah. And so theta was, again, if you neural network and whatever, forget about it, but theta was, again, if you're thinking about just linear things, it's just this theta m plus theta c. So you think about just fitting a line through a bunch of points. This is also fits into the same framework, right? So you have a bunch of points, xi, yi pairs, right? And you want to fit a line through them. So then again the problem is the same. You're trying to find, so you probably are using some mean square error distance. So you're saying that, okay, theta m xi plus theta c whole squared minus yi squared, right? Sorry, this. What to do? Sorry about that. Yeah, this, right? This entire thing, average over all of your xi's, take this thing, right? And minimize this. This is what you would, like, sort of one way you could phrase the problem of fitting a line through a bunch of points, right? Make sense? Yeah. So what we're doing is just a much more complicated version of that, right? So here this will again be your L theta, and of course you can actually just do gradient descent on this, and you will probably find some line which is kind of close. You can try that. If you want, you can write some really small amount of code in Python to maybe even try this experiment. But of course, in this case, you can actually optimize theta without using gradient descent, because this is a convex function and you can use, like, you can actually expand it out and apply all sorts of things. You can take the gradient comes out to be nice, and you can actually minimize things precisely, right? But in our case, the only part where things become complicated is that, our f is complicated, right? So our f basically looks like, again, going back to those slides, our f basically looks like this complicated thing, and it is doing some computation based on these things. So another very simple way of looking at it is, maybe this might be simpler for you, but if this is not, then ignore what I'm saying. It's taking some x vector and applying some affine transform on it. Because again, what you're doing is just weighted sum and then add some bias, right? And then you're applying some pointwise sigmoid function, right? And then you're repeating this pattern several number of times. And then this affine transform is going to have some matrix and vector, and these are your parameters, right? So these are your theta. Does that make sense? Okay, sure. So I'm guessing all of this makes sense to you. Right. Okay. So yeah, sure. Any other question? Oh, you're just the only one left here. Okay. No, that's fine. Yeah. So yeah, I guess if there's no other question, then right. There is a book linked, although the issue with the book is that of course, it being a good book. Yeah, go on. Right, so Sir will be back in campus whenever he is able to, because he has some personal emergencies that is going on. I have joined so I'm currently doing this, and I also have like a job at TRDS, so TCS Research. Yeah, so I'll try to come once, but and I can't give you any sort of guarantees at this point. So my location is Pune, so there is no permanent sort of teaching at CMI situation that I can use. Yeah. But I'll see. I'll try to come to CMI once and maybe. Yeah. Once things settle down for Sir, then Sir will be there on campus, so you can meet with him face to face. Yeah, sure. So okay, I'll so you can, at any point of time, you can mail me. You'll find my mail on CMI website. You can also message me via Moodle. I should probably say this when other people were there. But yeah, if you know someone who's also taking, tell them. If you want, I can also give you my WhatsApp number. That is also fine with me. I might not respond immediately, but you can definitely ping me there as well. You want it? I'll give it to you here itself, I guess. Yeah, sure. See, I don't want to put it out in Moodle because, anyone can look at Moodle. See, I can also go back and look at some Moodle of previous courses as well, right? But yeah, I can definitely take this in. You can also give it to other people who are taking the course and everything. So Harsh is the TA for this. He took this course and all the other courses by Sir last time as well. So he's been through this course once. You can go and talk to him as well. He's also really good. Yeah. So Harsh told me somebody was asking whether the course will be hard or not. Yeah, yeah, yeah. So I mean, I'll also tell you my angle on it. See, yeah, like the hard part of it won't be like, there's not going to be a lot of new. So there'll be some new concepts. Yeah, yeah. As in, see, it won't be intensive in the sense of new concepts, right? Like if you were to told, like, say, for example, um, GTOP 2 is intensive, right? But that is intensive in a different way. This won't be intensive in the sense of new concepts, because see, like these concepts are, at least what I feel is that, like, if you turn it over once in your head, it makes sense. Most of these things, right? It will be intensive in the sense that you'll have to do a lot of coding and exploration on your own, right? And we won't expect that to work out. So it's not like if you're, you write something up. Yeah, yeah, it's really fun, and that's what I told Deepakshita as well. Like, that it would be intensive in the sense that, you have to explore something, you have to try something out. We'll give you some suggestions. You try it out. If it works, then that will be something great. If it doesn't work, that's also okay, right? So as long as you're there and you're engaged in some sense, then that's fine. So it's, I guess the better term would be sort of like engaging in some sense, right? Like you'll have to do stuff, and it's okay if you get stuck. Just get stuck and tell us that, okay, I'm stuck. Then we'll be like, okay, yeah, sure. Then maybe this doesn't work. Try this instead, right? It's like that. See, because this is a really new field, there is, like, you can really quickly get very close to the bleeding edge of work that is being done. So we'll get close to that bleeding edge very quickly. So once we're at that bleeding edge, let's just touch it a little bit and see if we can do something. So yeah, right. So I'm sorry if I hopefully I didn't scare Deepakshita too much. Right. All right, sure. So if you have anything else, type, or I guess we can. Sure. Okay. So then, see you later then. Yeah. So next. Yeah. Sure. Thanks. Bye. I'll put up the sheet for all of the timings and everything.